Welcome. Exterior billiard is an extremely beautiful dynamical system. I got exposed to this very early on as a student when writing this lecture notes. I took the class of Moser on calculus of variation and wrote the lecture notes, and it's a beautiful discrete variational problem. Geometric setup is you take a table, a convex table, and what you can do is you take a point outside the table, and what you can do is you reflect it. So you reflect it, you take the tangent to the curve, and then you take this length is equal to that length here. So let me just maybe that. So that length is this length is equal to that length. So you reflect at that point. It's a dual billiard, sometimes also called cobilliard, outer billiard, exterior billiard. The question is, what happens in the long term? Is it stable? Does the orbit stay bounded, or does it go to infinity? Very beautiful problem. It has been popularized, especially in the 70s, by Moser in popular lectures like at the Institute of Advanced Studies or at ETH. Just in that article of Hasselblad, there is also an earlier reference to the 47, where one already has looked at the problem of periodic points. Joe Harris talked about Poincaré theorem, so that's also related with that topic. But the actual problem came then from Bernard Neumann, and actually group theories appeared first in print in an open problem collection. Then in Moser's book, Stable and Random Motion, it's kind of one of my Bibles as a student. And here is the lecture notes, Moser's course on selected chapters in the calculus of variations. So let's look at that. Moser just illustrated with this stability kind of thing. What happens when the table is smooth, then you get stability by KEM theory. It's not so easy, because what you have to do is you have to analyze the dual curve. So in this case, the dual curve is a lens type space, but for every convex curve there is a dual curve, and the orbits far away will be close to that dual curve. So this is dual curve. And what Duardi did, Raphael Duardi, the brother of Adrien Duardi, was in 1982 wrote a thesis and kind of carefully showed that this is enough to analyze this close enough that you can apply the KEM theorem, and so for sufficiently smooth R, I think you can go down to 3 nowadays, then you have invariant curves. But it's unknown what happens, say, for a C1 table. So in this case, this is not a C1 table. In this case, the first derivative is not continuous. So what happens in a C1 table? There's no unstable billiard known. So in the case of polygons, Richard Schwartz was found the kite. The kite is an example where you have instability, and there is a result of Piat-Bassan for the half circle. And actually that has been an observation which I had been already aware of early on as a student when Tabatchnikov actually, Tabatchnikov was in 1992 already made experiments with a half circle billiard, and together with Monroe, I think it was a student of his, has kind of seen some unbounded orbits. It's in the paper, you see the unbounded orbits. And I was, I think, around 2005 when giving a course here, 118, the dynamical system course. I was kind of made experiment just with a concrete number 2 plus I. And then you see very clearly outside, you see the orbits actually kind of circle around it, and in the next turn you see very clearly that the orbits become unstable. And actually, even statistically, you can look at that. Let's just take 100,000 points here and see what happens. I run 100,000 points and see what happens with the norm. You can describe this with in a complex plane. So what is the radius? What is the distance from the origin? And it seems that it's really very, very nicely bound between the square root of n times 3/4 and square root of n times 3/2. Very, very sharp. And so I think that's kind of my experimental contribution to this. It seems that this paper is very, the paper is not easy to, the proof of this is quite technical. It would be nice to have kind of an easy way to see that there is say for 2 plus I that you really go to infinity. But that's what I wanted to say today.